I want to take you back before we begin our discussion of the theory of relativity to remind you of Maxwell's equations. Maxwell's equations were 4 in number, 1, 2, 3, and 4, in addition to what is called the Lorentz force equation. The Lorentz force equation tells us that if we have a charge Q that's in an electric and a magnetic field, E and B, just sitting in the electric field or having any position, or moving with velocity v in a magnetic field, that the force that the particle experiences is given by this equation. This is then in turn equated to dp dt, the time rate of change of momentum, because you recall that F is equal to mass times acceleration, or better yet, dp dt. Now this tells us that given the electric and magnetic field, what's the force on a particle? But it does not tell us, given the particles, how they generate the electric and magnetic field. Now, previously we've discussed Gauss's law of electricity, where charges give rise to an electric field. Gauss's law of magnetism, which has no monopoles but only dipoles. Faraday's law of induction, which says that the time rate of change of a magnetic field gives rise to an electric field, and Ampere's law, modified by Maxwell, which states that if we have a changing, here's the d by dt, changing electric field, and currents can both give rise to the magnetic field. Now these 4 equations Maxwell then studied and came to the following conclusion. This was in chapter 33, and you'll recall that in this chapter we found that Maxwell solved these equations in a vacuum, meaning no charges and no currents were found anywhere, that there's still a solution where E and B are perpendicular fields, can oscillate at any frequency with any amplitude, but the E has to be proportional to the B. In other words, there's a proportionality in the amplitude of E and B. He also found that the speed of light was a constant, the 1 over the square root of epsilon naught times mu naught. And the light must move, the electromagnetic radiation must move with that exact speed. We talked about the form of the wave being a cosine, any amplitude, an angular velocity, a wave number, and a phase. And we talked about these various aspects when we talked about chapter 33 and the form that the electromagnetic wave would have. Now we're going to go to our current chapter, chapter 37, and talk about special relativity and the consequences of that. It's important for you to realize that in the year of about 1890, this is section 37.1, that in about 1890, many physicists felt that almost everything had been discovered. The world was seen as composed of 2 things: particles, which obeyed our customary laws of space and time, acceleration, where forces were given by the time rate of change of momenta. And then there was one other thing. There was electromagnetic waves. So 2 things existed. The electric and magnetic waves of Maxwell that were done about the mid-1800s, and Newton's work was done about the middle of the 1700s. I'll put 50 here to imply the middle of the century. So people felt like, well, that's all there is. And of course, everything was about to change drastically, because this was in conflict. The fact that C was a constant was in conflict with all of the thoughts of our space and time. It's not possible for anything to always move at the same speed. Then later we find that these waves are actually particles, and these particles are actually waves in quantum theory, which all of this happened in the beginning of the period 1900 up to about 1905. And on with quantum mechanics up into the year of about and of course it's continuing today, 1925, 1930. So what was this issue of a conflict between electromagnetic waves and particles? Well, as I mentioned before, the constancy of the velocity of light, the same that all observers see light moving at the same speed, is predicted by Maxwell's equations. Well, Maxwell did his work in about 1855. He was a Scotch physicist, and that's about the time of our Civil War. And if you compute this, it turns out to be very close to 3 times 10 to the 8th meters per second in a vacuum. Well, they didn't believe that. How is it possible for this something to go along like this wave? And if we're traveling at, for example, a velocity that's 90%, 0.90 c, and this wave passes us, it must go just by us by 10% of c. But no, it's found to go by us at c. And if we turn around and go at 90% c in this direction, wouldn't we expect it to see it going almost twice as fast as light? Well, it doesn't. It goes at the speed of light. And if someone sits on the ground, they see it moving at the speed of light. It's true for all frames and all observers. Michelson and Morley began doing experiments on this, and they proved that it was true using the Earth's motion. And this was done by a very, very classic interference experiment. They actually took a huge tub and filled it with mercury and floated a huge stone on that mercury in order to have something that they could rotate and move without any vibration or distortion. And this was like a grinding stone for corn, as I recall. They set it up where light would go down here, hit a half-silvered mirror. Half would go through, half would go this way. Reflect here, come back through, and interfere. If the distance or the speed of the light were different in this direction and this direction, it would cause different interference patterns between the light as it came back and interfered with itself. No such interference was found. This conflict was very serious because it basically said that in Newton's theory of space and time, the distance is equal to the position in another frame minus velocity times time. And that time in another frame is always equal to time in the first frame. This is the transformation between one frame, let's say sitting still, a frame x and t, and another frame of observation which is moving along, let's say x prime. And you can see that as x prime moves along, if we have a point here and it measures a position with respect to x prime, that x prime would that x would equal to the x prime. X would equal to x prime plus this distance right here. And this distance is, assuming that the two frames were coincident originally, if they started right here at t is equal to 0, it would be velocity times time. And of course I've inverted this to solve for x prime as x minus v times t. The distance x prime over to here is less than the distance of x over to here by this distance right here, how far the frame has gone since time t is equal to 0. And you can see from this equation here, if we divide by this equation and say, what is the change in x prime over the change in t prime for the observer who's moving, it would be equal to the change in this, just using simple calculus, change in x over change in t minus v over change in t over change in t, which is 1. And so the velocity in the prime frame is the velocity in the unprimed frame minus the relative velocity of the two frames. And this is absolutely confirmed and predicted by our classical physics, and it is wrong, according to all of the experiments that are done and the prediction of Maxwell. So what we had was a dilemma. The dilemma was this: do we accept Newton? Is Newton right with his ideas of space and time, and that things must differ in their speed? Well, that violates what we predict from electromagnetic theory, it violates Maxwell's theory, and it violates experiment, because this is not true at the speed of light. Light goes at the same speed with respect to everyone. So these two things are in conflict, and Einstein chose to believe this one. He said, I believe that Maxwell's theory is correct, that the transformations must be linear, and 2, between space and time, and 2, that c is equal to a constant. And so he proceeded from